Okay, we are in Unit 14, Graphing Trig Functions, Section 14.1, Chapter 6.4 in your textbooks, Graphs of Sines and Cosine Functions. Our objective is students will successfully sketch the graphs of basic sine and cosine. Yesterday I posted videos of me completing this. This is the sine curve. Again, the important points on a sine graph are 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and 2 pi. So if I was to hand sketch this on, the easiest is on notebook paper, I would draw my axes. I actually start at my 2 pi. I cut that in half, and halfway is pi. I cut that in half again. That is pi over 2. And then I have 1 half, 2 halves, 3 halves. And then I can put in 1 on each, positive 1 and negative 1 on the y-axis, and then I can go ahead and plot my important points. So 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, 2 pi, 0. And then I connect my dots in a curve. If you make any when you're making your line, you make any dots invisible, go ahead back and make them big again. That is our graph of sine. Okay. Next up is our graph of cosine, which again, yesterday I posted videos for this. So our important points are 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, 2 pi, 1. Again, you can graph this by hand, easiest on notebook paper. We're going to start at 2 pi. We're going to cut that in half with pi. Cut that in half with pi over 2. So now we have 1 half, 2 halves, 3 halves. And our x-axis is done. Our y-axis is 1 and negative 1. And cosine is 0, 1. Pi over 2, 0, pi, negative 1, 3 pi over 2, 0, 2 pi, 1. And then again, we're going to connect those points in a curve. We do not want this to look like a triangle, or pieces of a triangle. So there is y equals cosine theta. Okay. All right, so now, what are our domains of sine and cosine? So we want to think about what we are allowed to plug in on these two graphs. So can I keep going forever in the x-axis way? Can I go both directions forever on both of these graphs? Yes. So our domain is negative infinity to positive infinity, or in other words, all real numbers. Okay. We want to think about the range for sine theta. What is the biggest y value that you can have for sine theta? So if I'm looking at the graph, the highest that I go is 1. My next question is, what's the smallest value you could have for sine? Negative 1. And on our curve, or on our circle, I mean, remember our ordered pairs, of 1, 0, 0, 1, negative 1, 0, and 0, negative 1 are y coordinates are our sine values. So the highest that we can get is 1 and negative 1 there. So our range for sine is negative 1 to 1, square brackets, because both those values are included. Okay, now for cosine, what's the biggest y value? I wrote x here, sorry, that is a typo, this should say y. What is the biggest value you could have for our y values on here, okay, again 1 and -1. If we are talking about our unit circle, okay, our x values are our cosine for the ordered pairs. So 1 and -1. So again, our range is -1 and 1. Now, if I am looking at the unit circle and I am doing multiple laps around the circle to get higher angles, for instance, what if I asked you for the sine of 400? Well, that is 360 plus another 40. Okay. So and that would relate back to having the reference angle of 40 degrees. So because these trig functions are the same for repeated revolutions around the unit circle, they're called periodic. Okay. Meaning after a certain time, the values start to repeat. Okay. And we can see this with our graphs. If we were to graph this further, let me go ahead and do this on the calculator. So if I get y equals, I'm just going to do sine. I want to go to zoom, and I want to go to trig, because we're doing trig. The next important thing is to make sure that you're in radians, which I was. Okay, so here's my sine graph, and as you can see, it doesn't just restart here, but it also goes back this way. So it's repeating. And if I make my window longer, right now I'm going to -2 pi to 2 pi. Those are those values there. Okay. Let's say I go to -4 pi and I go out to +4 pi. Okay, I'm going to make this a little bit closer so we can see it better. No, we want our scale to be pi over 2 is our marks, and our y min, let's say -2, and our y max +2. So now let's look. So as you can see, this does in fact repeat. Okay? And where we start and stop at our repeat, that's called one period. Okay? So when we graph these, we are really just interested in that first period because we know it's going to repeat. So here, what would happen to the graph of our function f of theta equals sine theta if we were g of theta equals 2 sine theta? Okay? From what we know about graphing techniques, what does the 2 do? Is it a vertical stretch, a horizontal stretch, up 2, down 2, left 2, right 2? We need to think back to our parent graphs and what that does. So this 2 causes a vertical stretch by a scale factor of 2. Okay? So, again, we want to start with our parent graph just like we've done with every other graph that we've done parent graphs with. We want to think about our important points. I already have it here just to save some time. So now I'm going to go to my important points, and we're doing a vertical stretch. So 0, 0 does not change. Pi over 2, 1 is going to change. The vertical distance is currently 1. I multiply that by my scale factor of 2. So 1 times 2 is 2. So I'm going to be at pi over 2, 2. Distance from our x-axis is 0. So 0 times 2 is 0. So that point does not move. 3 pi over 2, -1. Vertical distance is -1 currently. Multiply by our scale factor of 2, we get -2. And again, 0 is not going to move. So now, the graph of this function of g of theta is that. Okay, notice we've stretched the graph vertically by a scale factor of 2. Okay, next one. Now we're going to look at cosine theta, and we want g of theta to be negative 1/2 cosine theta. So we need to think, what does the negative 1/2 do? Okay. So the half vertically shrinks. We have a vertical shrink by a factor of 1/2. The negative out in front causes a vertical flip. And a vertical flip means a flip over the x-axis. So we have a flip over the x-axis. Again, just like all parent graph graphing, we need to have our parent graph first, which we do have. These are our important points, and these are what we're going to focus on. Okay. So we're going to take our vertical distances and multiply them by 1/2, and then instead of up, we go down. Instead of down, we go up. So at 0, 1, vertical distance is 1. 1 times 1/2 is 1/2. Instead of up, we go down 1/2. 0 times 1/2 is 0, and it's 0 away, so zeros are not going to move. Pi and negative 1. Negative 1 is 1 away, so 1 times 1/2 is 1/2. Instead of down, we're going to go up. Okay. 3 pi over 2, 0 is not going to move because 0 times 1/2 is 0, and it'll flip over the x-axis. It's on the x-axis, so it doesn't flip. Okay. Pi over 2, 1. 1 times 1/2 is 1/2. Instead of up, we're going to go down. Okay. So our g theta function, and again, I have a hard time drawing them like this. If you want, you can turn your paper sideways, and you typically get a better curve going sideways. Okay. But this purple line is our g theta function. Okay. Now, we see that these graphs stay a certain distance away from that x-axis, and we have a name for that. Okay. Half the distance from the maximum value of the function to the minimum value of the function is called the amplitude. For y equals a sine theta and y equals a cosine theta, the amplitude is the absolute value of a. So in this case, y equals negative 3 cosine theta, we want to know the amplitude. Well, our a value is negative 3. So our amplitude is equal to the absolute value of negative 3, which would be 3. Okay. Our amplitude for y equals 1/2 sine theta, I'm going to abbreviate amplitude. Okay. Our amplitude is the absolute value of our a. Our a is 1/2, so the absolute value of 1/2 is 1/2. In other words, these are asking us how far are we away from this center line. Okay. So, looking at the equation, we can get that. We can also get that from looking at the graph. All right. As we've already mentioned, if you continue graphing y equals sine theta past 2 pi, we get repeats. Okay. And what would happen if we continued on to 6 pi for our x-axis? Well, we would fulfill another period. Okay. This is because y equals sine theta is periodic. In other words, after a certain point, y equals sine theta starts to repeat itself. When does it start repeating itself? So, at 2 pi, so we call it the period for the sine function is 2 pi. What happens when you continue graphing cosine theta past 2 pi? Well, again, it's going to repeat. And what do you think would happen if we continue to 6 pi? It would repeat more, another time. And again, it's because y equals cosine theta is periodic. In other words, after a certain point, y equals cosine theta starts to repeat itself. When does it start repeating? At 2 pi. The period for the cosine function is then 2 pi. Okay, what would happen to the graph of our function, f of theta equals sine theta, if g of theta was sine equals 2 theta? Remember, we're thinking about theta as like our x, so this 2 is inside with the theta. So what we know about is inside affects the graph horizontally. So from what we know about graphing techniques, what's the 2 do? Remember, inside is inverse. So the 2 is a horizontal shrink by 1/2. Okay, now what we have to think about is the period of sine. We just said the period of the original sine function is 2 pi. That's for f of theta. Okay, for g of theta, if we're horizontally shrinking this by 1/2, what do you think g theta's period is going to be? We're going to cut the 2 pi in half. So that means we're going to be at pi. Okay, that's where our repeat is going to start. So this shrunk down into this section. Okay. Now for these, I do horizontal shrinks a little bit different. So I'm going to take my period, and I'm going to, because we always start at 0 for the period, beginning of the period, right? I'm going to go 0 and pi. I'm going to cut that in half. What's half of pi? Pi over 2. What's half of pi over 2? And that's going to be pi over 4. Half of a half is a fourth. So now I have 0, 1/4, 2/4, 3/4. These are going to be my x values, or in other words, my theta values for my important points. My important points for sine are 0, 1, 0, -1, 0. Okay. So 0, 0. Pi over 4 is here. So pi over 4 is 1. Pi over 2 is 0. 3 pi over 4 is -1. And pi is 0. Now, I personally think graphing horizontal shrinks and stretches are difficult when you put it on the same graph as the parent function. So you can write this out, but this is how I do it. I don't graph the parent function. Okay, I still do my 1 and -1, but then I look at my period that we found of pi, and I start with pi. I actually do this chopping that we did on the graph. So pi, cut it in half, is pi over 2. Cut that in half, pi over 4. So now I have 1/4, 2/4. My next chop is 3/4. Okay. And then I know sine always starts down at 0. It swings up to 1. It comes back down to 0. It goes down to -1 and swings back up to 0. And then I'm going to go ahead and turn this a little bit sideways. And then you sketch your graph. Okay, so this is our g of theta. All right. Okay, let's try another one. What would happen to the graph of f of theta equals cosine theta if g of theta was cosine equals 1/2 theta? What does the 1/2 do? Remember, that's inside with our theta. So inside affects the graph horizontally, and it's multiplication, so that means we have a horizontal stretch by a factor of 2. Okay. Again, we want to know our period for f of theta. So f of theta period, it's cosine. Cosine's period is 2 pi. So our g of theta period, okay, is what? Well, if we're horizontal stretched by a factor of 2, that means it's going to take the period and stretch it by a scale factor of 2. So 2 pi times 2 is 4 pi. Okay. Now, on our graph of our parent function, we can't graph that. So we have to go back and do our own graph. Again, we know it starts at 0. We know our first period is going to end at 4 pi. We only want to graph one full period. So we don't have enough space on this one to graph it. So now we're going to go back to doing our cutting again. Cut 4 pi in half, so that's 2 pi. Cut 2 pi in half, that's pi. So now we have 1 pi, 2 pi, 3 pi, because all of these increments are going by the same amount. Okay. Cosine g of theta has no vertical stretch, so our y values are still the same. We have to remember that cosine starts up at 1 and drops down to 0 and then -1, 0, 1. So we need our y values here. So we start 0, 1, drop down to pi, move down to -1, move up to 0, move up to 1. Again, I'm going to turn this sideways so I can sketch it nicer. Notice my graph has curves. It does not look like the sides of a triangle. They should not be straight lines. All right. So if thinking about it logically is a little bit difficult for you, I have ways of doing it equation-wise. Make sure I got this on the screen. Okay. For y equals b theta and y equals cosine b theta, so b is acting as that coefficient of theta in both these cases, the period is 2 pi divided by b. So we're taking our original sine cosine period and dividing by that coefficient up front. Okay. So what's the period of the following function? So first, what's our b? In this case, our b is 4. So we're going to take our old period, 2 pi, and divide it by the 4. So reducing that, we get pi over 2. So if I was to graph this thing, I would start at pi over 2 and then start cutting it into halves. So half of pi over 2 is a pi over 4. Half of pi over 4 is pi over 8. So then I go 1/8, 2/8, and this mark is 3/8. Okay. All right, for y equals sine 1/3 theta, our b is 1/3. So I take our 2 pi and I divide by 1/3. So I keep, change to multiplication, and flip. So our new period would be 6 pi. Okay. Again, for graphing that, I would go 6 pi, cut that in half, 3 pi, cut that in half, 3 pi over 2, and this is where it gets a little bit difficult. You may want to think about this as 1.5 pi, 1.5 pi, 3 pi, I add another 1.5, so that would be 4.5 pi. we don't want to write it in this decimal form. We do want to write it as a fraction, but it's easier for us to think backwards into fractions from this. This would be 9 pi over 2, and then 6 pi. Okay, so this unit is really important that you understand fractions, and that you can switch back and forth and understand how to work with fractions. Okay. What would happen to the graph of f of theta equals cosine theta if g of theta was cosine equals theta plus pi over 2? So in other words, what does this plus pi over 2 do? It is on the inside, so that affects the graph horizontally, okay, which means inside is inverse, so we are going, it looks like a right, but we need to inverse that, so we go left pi over 2. Okay. So now, this is our parent graph. I'm going to go ahead and graph it above this. But I need more room. Okay. So, my units that it's normally 2 pi, when I split them up, my marks are pi over 2 away from each other. So really, if I do 2 pi, cut it in half, pi over 2, 1/2, 2/2, 3/2. All I need is one more of these units this way, and that's my pi over 2 that I'm going to be moving. Okay, so my vertical has not changed. So cosine starts up at 1. So that value is going to move left pi over 2. This value is going to move left pi over 2. This value is going to move left pi over 2. This value at 3 pi over 2 is going to move left pi over 2. 2 pi is going to move left pi over 2. So, let me sketch that. So now, if I was just going to look at just that, doesn't that kind of look like one of our other graphs that we've done? If I continue this further, because we know we can, what graph does that look like? Okay. Hopefully you are saying y equals sine theta. Okay. Remember, one of our cofunctions was that cosine theta plus pi over 2 was equal to sine of theta. Okay. This is purely because of shifting of the graphs. That's where that property comes from. And at the time, I told you, you just had to believe me that this was true. But now, graphically, we can actually see it. Another shifting example. Make sure I have it on the screen here. Okay. What would happen to the graph of f theta equals sine theta if it was g theta equals 1 plus sine theta? So this 1, what is it doing? Well, is it on the inside or is it on the outside? That's on the outside. So that is a vertical transformation. We don't write plus 1 at the end. We write it at the beginning so we don't have confusion that it's in with the theta. So this plus 1 means it's going to be moving the graph up 1. So up 1. So everything is going to move up 1. So this point moves up 1. 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 Okay, so again, I'm going to turn this sideways just so I make the graph look a little nicer. Okay. So I have this graph is my g theta. Now, if I was talking amplitude on this one, okay, my coefficient in front of sine is still a 1. So my amplitude should still be 1. Don't get confused because it looks like it's a 2. You have to remember we moved the x-axis, if you will, up a whole unit of 1. So if we think about our x-axis being here, our amplitude is still 1 away. Okay? Alright. For general sense, y equals d plus sine theta and y equals d plus cosine theta, the graphs of the functions are moved vertically d units. So if it's a negative, it's going to move down. If it's a positive, it's moving up. Okay. All right. What is happening to these? That's our essential question. So our 7 is on the inside, so that is a horizontal, and it's multiplication, so that's a stretch or a shrink, and remember we do inverse, so this is a horizontal shrink by 1/7. So that means our period, we would have 2 pi divided by 7. Okay. The 5, that's on the outside. It's not multiplication, so that is an up or a down. It is positive, so we are moving up 5. Okay. And in our last one, we have a little bit of everything. So our pi is on the inside. It is addition, so the inverse would be subtraction. And it's inverse of what we think. We normally think plus is right, so that means we are moving left pi. The 3 on the front end, that is multiplication, so that is a vertical. And since its multiplication is a stretch or a shrink, so outside acts normal, so it's a vertical stretch by a factor of 3. Okay. Your homework is page 495, 1 through 25 odd, 27 through 34 all, 35 through 63 odd. Okay. And don't get too upset. I do expect some difficulty with the graphing. Make sure that it's, like I said, it's much easier to graph these on notebook paper rather than graph paper, just for the sense of getting being able to draw your own units out. Okay? So, I will talk to you again soon.